Hi everyone, my name is Sarah Kane. I am a PhD student in astronomy at the University of Cambridge, and I am one of the co-instructors for this non-visual data science tutorial series alongside Patrick Smith, who is a blind programmer and programming instructor and consultant with the IOTA School. This is the fourth of the 5 tutorial series. Today we'll begin talking about data sonification, and the next tutorial, next week, will also cover the same topic. Again, these tutorials take place Tuesdays from 6 to 8 p.m. UK time, that's my time zone, 1 to 3 p.m. Eastern time in the US, or whatever that corresponds to in your respective time zone. These tutorials are being very generously supported by Pandas and NumFocus, which makes them free and available to all of you. And all of the materials, including this recording you're watching right now, and all of the written curricula are online and available to you. I really encourage you to check out the curriculum. It's got all of the code we'll go over, as well as some more details and written instructions for everything we're doing today if you want to revisit it in written form. And of course, Patrick and I are always happy to answer your questions over email. We also have office hours on Thursdays from 6 to 8 p.m. UK time, 1 to 3 p.m. Eastern time in the US, and so on and so forth, over the same Zoom link that this live tutorial occurs. Now, those of you who are watching this right now might be able to tell that this is not a live Zoom course happening. We're currently this is not the royal we, but I am currently re-recording this tutorial. We had some unfortunate sound difficulties during the live Zoom, so we wanted to make sure there was a nice clean version with no sound difficulties available to everyone for posterity, so to speak. So I'm excited to go over this curriculum again with all of you. And again, if you have questions, please feel free to reach out. Now, without further ado, especially because there's no one else here with me, I think we're just going to jump right into things. So as you have before, I encourage you now to open up Anaconda prompt. I'm already on the screen. I'm going to turn on my NVDA speech again. Didn't want it talking over me during the intro.
Speech mode beeps. Speech mode talk.
Excellent, and hopefully you can hear that okay. Okay. So open up Anaconda prompt as we have in the previous 3 tutorials. If you are not already there like I am, you can do that by hitting the Windows key and typing in Anaconda prompt to open it up. Again, this is Anaconda prompt, not Anaconda Navigator. And what I want you to do right now is not to start IPython. Again, please do not start IPython yet. Which is what we do usually after opening Anaconda prompt, because that's the sort of interactive workspace we have to write code and test it. But what we're actually about to do right now is to do something called installing a package. Now, we've used packages in the previous tutorials. We've used Pandas and NumPy. These are like libraries of code that other people have written that we can now make use of. And those packages, because they're really popular and widely used, are available with the Anaconda installation that you already have. But some less common packages, like astronify, which is the sonification package that we're going to use today, is not already pre-installed with Anaconda. So we're going to have to install it ourselves. No worries, it's pretty simple. It's as simple as one line of code, actually. But before we get into that, I want to just go over a few caveats. First of all, unfortunately, to our knowledge, we really only expect the Astronify installation to work properly on Windows computers and also maybe on older MacBooks. If you have a MacBook with one of the newer Mac chips, so not an Intel chip, but a Mac chip, so that's the M1, M2, M3 Mac, we have had no luck getting Astronify to work on those new Macs. Likewise, if you are a Linux person using Linux, unfortunately, we also have not had luck getting Astronify to work on Linux. This, alongside our desire to use NVDA as the screen reader we're teaching with, is kind of one of the motivations for us encouraging all of you to use Windows for this tutorial series. Also, if you have other packages already installed, so say you already program a bunch and have other things installed on your Anaconda, it is possible that this might not work. It's really hard to predict how different package dependencies might not get along with each other, might not work out properly. So if you have some sort of error message because you have other packages already installed, please do let Patrick and I know, either in office hours or over email, and we will try to help you out. But for the vast majority of you who have installed Anaconda nice and fresh for this course, this should be quite simple. We hope anyway, cross your fingers. So installing Astronify, and I've uninstalled it actually so that I can install it with you now, is as simple as one line that we're going to type, again, not in IPython, just in the Anaconda prompt. We are going to type pip, P-I-P.
P-I-P.
Pip is our package manager here. It's the one managing all these libraries of code. Pip is the thing that's going to install this package for us. There's another package manager out there called Conda. Some things are available via Conda, others via Pip. We won't get into that. This one, we're going to use Pip. And if you're curious, check out the curriculum online where I talk about it a little bit more. So it's pip, P-I-P, space, install,
I-N-S-T-A-L-L.
pip space install space astronify. A-S-T
Space A-S-T
R-O-N
R-O-N
I-F-Y.
I-F-Y.
Pip install astronify. A-S-T-R-O-N-I-F-Y. And hit enter.
Collecting astronify. Using cached astronify 0.1 pi3 non-any.whl. Requirement already satisfied. Astropy in C. Users.
All right, so I'm going to stop that now because there's a lot of text happening there. So I don't want you to hear all of it, but I wanted some of it to play because I don't want you to feel like alarmed when NVDA starts reading out just this absolute barrage of text. It should mostly be along the lines of like requirement already satisfied, installing XYZ. If you start getting some angry sounding messages like, couldn't do this or whatnot, that's a good time to start maybe doing some Googling or contacting Patrick and I. But hopefully it'll all be nice things that are like requirement already satisfied, and it should end with successfully installed Astronify. And that should be all you need to do. Occasionally, I think I've seen some people get a message where it says proceed ? Yes, Y/no, and you have to hit type Y for yes and then hit enter. I don't think most of you should get that, but if you do, not to worry. And with that, congratulations, the Astronify package is installed. Cool. Done. First module or first section of this curriculum or of this tutorial is checked off the list. What I'm going to do now is I'm going to actually step away from the terminal, step away from some code, and give you a little bit more theory about what sonification is and how it works, because I know I've just mentioned sonification a bunch of times here without actually saying anything about what it is. So we're going to get into the theory, we're going to get into the examples, and then we'll get back to the code. Yeah? On that note, I'm going to turn off the speech for NVDA so it doesn't decide it wants to talk over me or talk over any of the sonification examples, which we did have a little bit of in the original Zoom. So, this is one sound issue we will dodge.
Speech mode off.
All right, and with that, we will get into what is this sonification thing. So in the simplest terms, sonification is the representation of data via sound. This is directly analogous to data visualization, where data is represented via some visual medium. These are your line charts, your bar charts, your pie charts, your histograms, the list goes on. There are a ton of data visualizations out there. Importantly, the data does not literally look this way. It does not literally look like a line graph. It doesn't look like a bar chart. This is how we choose often to represent it, through some visual medium. And in fact, there are a lot of arbitrary choices involved in these visualizations. For instance, You have a line chart. How are you going to scale the axes? How large will you make the points? These are all various different choices that you can make in these data visualizations. It is a representation of the data, a way we choose often to picture the data. And oftentimes they're quite useful. They let us understand trends and things like that, but there are issues with data visualizations, and not the least of which will be, of course, great interest to me and you, is that they're not accessible to people with visual impairments like me. So, data sonification, where we represent the data as sound, sort of corrects or steps around that sort of problem. Now, before we get more into data sonification and what exactly a sonification could be besides this sound representation of data, I want to break down some common misconceptions about sonification. First of all, sonification generally doesn't involve words, so it's like non-speech audio. So for instance, me standing here and telling you about data, for instance, when Patrick told you about the Airbnb data set, that is not a sonification. It's just him telling you about the data. So it's not typically what we'd consider a sonification, a sound representation of the data. It's like a word representation of the data, something along the lines of that. I don't have a more elegant word for that, but it's not generally what we'd consider sonification. Sonification also is not what we'd consider like natural sounds or just the sounds themselves. What do I mean by this? Well, for instance, imagine you have someone walking and you are listening to their footsteps to understand, to measure how quickly they are walking. In this case, the sound of their footsteps is not a sonification. The sound of their footsteps is the data. So the sound is not a representation of the data. The sound in that case is the data. Scott Fleming, in his talk at the Space Telescope Science Institute's Day of Accessibility, had another great example. Bird songs, not a sonification. Bird songs would be your data if you were going out and observing bird songs. Same sort of idea here. So it is in the same way that a data visualization is not literally like what the data looks like, a data sonification is not literally what the data sounds like. All right, so we've broken down roughly what sonification is. It's a sound representation of the data, and it's not words and it's not sounds from nature. Okay, we got the big picture here. The only way to concretize this sort of idea of what sonification is going to be to get into how we actually sonify things. Today we're going to go over two of the most common sonification techniques. This is going to be audification and parameter mapping, what they are, what their differences are, and we'll also talk about we'll also show some examples of each. All right, let's begin by talking about audification. You'll often hear audification described as the most direct mapping, the most direct representation of data as sound. What do we mean by this? Well, suppose we have two variables here, x and y. And in this case, y is our dependent variable, which means that as x changes, y changes in response. Now, for our purposes here, I'm going to say x is time. So as time goes on, y changes with time. And so if y is varying with time, going up and down as time goes by, you can kind of imagine y moving like in a regular wave, not like a smooth wave pattern, but it's going up and down. So y, the height of the wave, is changing with time. Now we call the height of a wave the amplitude. And just as this height, this amplitude of y is changing with time, we can imagine the amplitude of a sound wave changing with time at the same sort of way. So basically, if y goes up, the amplitude, the height of our sound wave goes up, and if y goes down, the amplitude or height of our sound wave goes down. So we are mapping the height of y to the height of the sound wave. This is what we mean by direct mapping. We're treating y like it's a wave and then just making the sound wave that represents y behave in the exact same way as y in terms of how it goes up and down. Now, our ears perceive amplitude, the height of the sound wave, and again, sound is a wave in the air, so our ears perceive the amplitude of a sound wave as the volume. It has to do with like this air pressure. Essentially, you'll hear it as changes in volume. And so essentially what is happening is by going up and down, y is controlling the value of, the volume of the sound wave we hear representing the data. All right, so we've covered how the volume is controlled by y. What about pitch? That's another really important part of sound, how high or low a note is. Well, this comes down to something we call data sampling. We don't measure data continuously. Rather, we have some sampling rate, which is often how we measure the data. So for instance, I'm going to play you some sounds from the Accessible Oceans Project, some audification from the Accessible Oceans Project, and the tides are measured each hour. This is our data sampling rate. So we have like 24 measurements in a day, one measurement each hour. Likewise, we don't play the sound continuously, but rather we play it at some data sampling rate where we play each note at an individual moment. So we have our data measurement rate, or data sampling rate, and we have an audio sampling rate where we play the rate at which we play the sounds. Now the sampling rate, or the frequency at which we measure and then play the audification of data, is analogous to sound frequency, which our ears perceive as pitch. Thus, the frequency of the sound playback influences the pitch at which we hear the audification. Often, we cannot play the audification of the data with the same frequency as the original data sampling rate because then the frequency or the pitch we'd be playing would just be outside the audible hearing range for humans. Thus, in audification, we often have to do something that I've seen called translating or shifting the sound representation of the data, how the sampling rate at which we play notes, just so that the pitch is in the audible pitch range. Now, what I'm going to do is I'm going to play you a sonification of the tides from the Accessible Oceans Project at 2 different sampling rates. It might be a little bit difficult to hear over the recording, like from my computer to your computer, but there are 2 different sampling rates, and you can hear that there's a pitch difference between the 2. If you can't hear it through the recording, I do encourage you to go from the tutorial curriculum page to the Accessible Oceans page, which is linked there and has the examples on it. So if you can't hear the pitch difference here, definitely encourage you to go check that out. I'm going to go play that now, so it'll be 2 sonifications. All right, that was pretty quick, so I'm going to play that one more time. All right, hopefully you could hear the whoomp, 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 whoomp noise happening there. That is the tide cycle you're hearing. So tides go in and out, every 24 hours. That's at least as much as I know about oceanography, tells you what I know. And so what you're hearing is that actually every 24 samples, not that we can hear the individual notes because they're so close together, you hear that whoomp, 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 as the tides going up and down control the volume of the audification going up and down. That whoomp, whoomp, whoomp. Each of those cycles is that 24-hour cycle of the tides going up and down. Now I'm going to play this one more time, the same audification, before I play the next one that's at a different sampling rate, so you can hopefully hear the 2 pitches side by side. All right, hopefully you could hear that. On my end, I can definitely hear the pitch difference. I'm hoping it comes through on the recording, fingers crossed. So what you might have been able to tell on those two is first that whoomp, whoomp, whoomp is still there because we're still measuring that same tide, or we're still representing that same tide data of it going up and down. The pitch is lower on the second round of data, and also it's a little bit slower. It's a little bit slower between each whoomp, 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 and the audification lasts a little bit longer because the data sampling, the frequency at which we play those notes is a little bit slower, which lowers that pitch and also lengthens the time of the audification. So again, hopefully you could hear that difference, and if you couldn't, definitely recommend checking it out on your own computer. All right, so if audification is so straightforward, we're treating the data like a wave, and then, actually, one second before I keep going, I think the computer is about to die. And rather than suffer another technical difficulty, which would make me quite sad, I'm just going to plug this in. Sorry, folks. All right, we're back in business. Okay, so if audification is so straightforward, where we're really just treating the data like a wave and then representing it as an analogous sound wave, why don't we do it for everything? Well, there are a lot of reasons. First, it's pretty limited in what we can or cannot sonify. For instance, how would you audify, make an audification or a sonic representation using audification of an image, of some 2D data, with an X and a Y and a colors? There are too many different parameters going on there to put into this amplitude, so this volume, and then the time. So it's really better suited for a very specific type of data, a simpler type of data. Also, there might be other reasons we don't want to use audification. For instance, maybe there's a more aesthetically pleasing, a nicer sound that we can use rather than these amplitude changes in the sound wave. An aesthetic difference is a really valid reason to have a different representation of the data. I mean, I can say that I know a lot of scientists that spend a lot of time trying to make their data visualizations look nice, look pretty. So that matters as a choice too, and it's a totally valid choice to make. Again, we're not literally showing what the data sounds like. We're making choices of how to represent it. And depending on our audience and our goals, we might make different choices. So let's get into what one of those different choices might be. And that might be to use a very popular and very flexible sonification technique called parameter mapping. Parameter mapping is a more flexible, as I mentioned, form of sonification that has become popular in recent years. And in parameter mapping, in essence, we map or connect different aspects or dimensions of the data to different parameters of the sound representation, such as pitch or volume and rhythm. Like audification, we could use parameter mapping to sonify data consisting of, say, one independent variable, that's what I called y, and one dependent variable, that's what was time for us here. But one of the strengths of parameter mapping is that we can actually represent with sound much more complex data than we can with audification, because there are many more aspects, parameters to the sound that we can use. That's pitch and rhythm and volume, different instruments and timbre. I'm not a musician, but the list goes on. There are a lot of different knobs we can turn in our sound to represent different dimensions, different aspects of our data. All right, let's clarify the concept of parameter mapping using an example. Suppose you have measurements of number of sales of something. I'm going to go with ice cream because I like ice cream. I could totally go for some right now. And net profits from those sales of ice cream over a period of 50 years. We choose to map the number of sales to pitch such that more sales are represented by higher pitches, and to map net profits to volume such that more profits are represented by a louder note. So essentially, we let pitch be mapped to sales, and volume be mapped to profits from those sales. And now we're letting time, that independent variable, what we'd have along, the x-axis if this were a visualization for any visualization folks, we let time be represented by time in the sonification, such that each note is a measurement in time, so that if you're listening later in the sonification, you're hearing later in time. So the first note represents 50 years ago, and the last note of the sonification represents the data measured now. Suppose, as we listen to the sonification, that we hear a period in which the pitch of notes drops, so the pitch goes down. We can tell from the mapping decisions that we made that this means that the number of ice cream sales in this period has dropped relative to the other measurements. Perhaps it's wintertime or a recession and people aren't buying as much ice cream. Now suppose that over the course of the entire data sonification, we hear the volume of notes generally increase, but the pitch remains relatively constant. This means that profits have gone up, but the number of sales has remained relatively constant. So the cost per ice cream sale, the profit per ice cream sale, must have gone up. That's what I'd call inflation. Finally, suppose that the amount of time between notes decreases towards the end of the sonification. This might mean that the data were collected more frequently in later times, so that there's less time between each data point. Note here that there is no one correct way to map our data to different parameters. We could just as easily have mapped sales to volume and profits to pitch. Thus, we make choices, generally through testing and experimentation, to see which representations of our data most effectively and most accurately capture the importance of information and communicate it, preferably in a way that's both understandable, comprehensible, and aesthetically pleasing. This is truly just no different from a data visualization, where graphics will go through many iterations of designs to clearly represent the data. Data representations, whether sonic or visual, always represent choice. So one of the things I hear most often about sonifications is that they're arbitrary, is that, this isn't, there are so many different ways you could represent the same data. How do you ever know anything? Because you could just represent the data so many different ways. But this is just how representations of data in general go. It involves choice. It's kind of a fun thing. All right, let's actually listen to a sonification or to a parameter mapping example. Now, because my background is in astronomy, we're going to listen to an astronomy example. This is from the NASA and Chandra X-ray Center's Universe of Sound website. And what we're going to do is we're going to listen to the sonification, but it also comes with a description which tells us how the parameter mapping was performed. So we're going to read that first, break down the parameter mapping, so what aspect of the data was mapped to which parameter of the sound, and then we'll listen to the sonification. All right. So we're going to listen to a sonification of the galactic center, or of data from the galactic center. This was taken from the Chandra X-ray telescope, I believe. Explore the center of our very own Milky Way galaxy. The translation begins on the left side of the image and moves to the right, with the sounds representing the position and brightness of the sources. All right, we've already got our first parameter mapping. The translation begins on the left side of the image and moves to the right. They don't say this directly, but what this means is that time within the sonification is mapped to how far we are moving from left to right in the image. So if you hear something earlier in the sonification, it's closer to the left. If you hear something right at the end of the sonification, later in time, it's representing something on the right of the image. The light of objects located towards the top of the image are heard as higher pitches, while the intensity of the light controls the volume. All right, that's two more parameter mappings there. So pitch is controlled by how far we are up and down the image, with higher pitches representing objects higher up in the image, so closer to the top, where lower notes are going to represent objects lower down in the image. We also have a second parameter mapping in the sentence. The intensity of the light controls the volume. What this means is that brighter objects are going to be represented by louder noises, and dimmer objects in the image are going to be represented by softer noises. Stars and compact sources are converted to individual notes, while extended clouds of gas and dust produce an evolving drone. What does this mean? Well, smaller objects are going to be little notes, larger objects, longer sounds. So the size of the object has to do with the duration of the note. The crescendo happens when we reach the bright region to the lower right of the image. This is where the 4 million solar mass supermassive black hole at the center of our galaxy, known as Sagittarius A star, resides, and where the clouds of gas and dust are the brightest. All right. I'm going to hit play. Hopefully. Super pretty, right? I love that sonification. That's one of my favorites. The Universe of Sound project has lots of sonification, so I definitely recommend checking it out. You can get a super long crash course into parameter mapping. I think they're lovely, really lovely to listen to. I'm biased because I like space, but there you have it. I don't know about you, but I think for me the easiest thing to pick out is that note duration thing. I can definitely hear those little chimes that are representing stars, and then the longer notes, especially towards the end where they told us that supermassive black hole is. I can hear that sort of longer stretch of notes. Really lovely. I recommend, if you want, to go and listen to that maybe several more times, see if you can hear those individual parameter mappings, the pitch representing how high we are along the image, up or down, the volume representing how bright something is. I definitely recommend that. I think it also probably would be easier to hear over your own computer, again, rather than through this recording. Though I'm hoping, fingers crossed, that the sound records much better here than it did for everyone else. Ooh, sorry if you hear some background noise. My guide dog is standing up and shaking. But I'm hoping it records much better than it did during the original Zoom. All right. So that is audification and parameter mapping, the two, I would say, most common sonification techniques you will encounter. That's also a really quick crash course into what sonification is. Just keep in mind, again, sonification is a sound representation of the data. Now, if you're sitting here and thinking, Sarah, it's super pretty, I think it's cool, but how in the world do you ever learn to interpret that? Very understandable. And especially it's understandable given that we think of data visualizations, graphs, and charts, and line graphs, and so on and so forth as intuitive and easy to interpret, but that is not at all true. Children in schools spend years learning to read graphs. In the US, where I'm from, there's a standardized test for college, like to get into university, called the ACT, and a whole section of the thing is basically reading graphs, and kids study for months for that. So clearly we need to learn to read and interpret data visualizations, and there are studies suggesting that the same should be expected to be true of data sonifications, that we should expect to need to learn how to understand and interpret them. This kind of makes sense. No one's born learning to read a data visualization. No one's born learning to understand, like already knowing how to understand a data sonification. So our goal for the rest of this tutorial recording is going to be to get some basic shapes in Python, and then to sonify those different shapes with that astronify package that we just installed in such a way that we can sonify those different shapes and understand how they sound. So you can hear, this is how a straight line sounds different from a curve, which sounds different from something that's moving in sort of a wave-like shape. The goal here is to develop some intuition for you so that things sort of make sense a little bit more on a natural level, so that next week when we get into sonifying some more realistic data, something that's not just shapes and lines, you'll have this intuition, or at least the beginning of an intuition, already built. So that's the goal for the rest of today. So now we're going to return to Anaconda prompt, or maybe you're already sitting there, and I'm going to turn NVDA back on.
Speech mode beeps. Speech mode talk.
And now we can start IPython.
I-P-Y-T-H-O-N.
So just as we have before, I'm going to start IPython by typing I-P-Y-T-H-O-N, IPython, no spaces, and hitting enter.
Python 3.1.1.5 packaged by Anaconda Incorporated. Main, September.
All right, I'm not going to let it play that whole thing through because I think you've heard it before, but essentially you'll know you're in IPython because it'll tell you your Python version, and eventually you'll get to it. If you let it finish, it'll tell you we're in 1. We're in the first input line. Now, we're going to start by making some of what I'm going to now refer to as synthetic or simulated data. What this basically means is it's not like real data from like observations or measurements. This is basically like fake data we've made to follow various shapes, or if you're math savvy and remember like your high school algebra classes, we're actually going to just be making some simple algebraic equations here. We're not actually going to go through making all of them. We're going to go through making several of them so you get the idea of like how this math is going to work. And then there's a CSV file that has everything already made that you can load in from the URL. I encourage you to go to the curriculum. It's under data preparation under the final subheading called just in case. Quote unquote. Basically, it gives you the CSV file in the URL and just gives you the code to paste it in. Yes, so I encourage you to do that, but if you're interested for how exactly all of that synthetic, so again, all of that not real measured data was made in the CSV file, the curriculum goes into painstaking detail about how every column was made and exactly the equations that's going into it. So we'll kind of do a brief intro to that just so you have a rough idea of how this CSV was made, but if you want all the nitty-gritty details, the curriculum has everything. All right, so those of you who remember algebra classes will remember that like functions, equations have 2 different variables. What I've called independent, or x, and dependent, y. So y is a function of x. Y is going to change when x changes. So what I want to do first is I want to make an array of numbers that's going to be our x values. So imagine all of these values. So I want, in our case, I want 100 values evenly spaced from 0 to 10, so that at each value of x, going from 0 to, I don't know, 0.1, 0.2, 0.3, whatever the even spacing will be, we'll have y change, a different value of y at each of those values, and that y will change differently depending on what function we do. Now, as was evidenced by the fact that I had to already sit and think about like the first 3 numbers and those numbers ranging from 0 to 10, I really don't actually want to sit here and write out a list or an array of 100 numbers evenly spaced from 0 to 10. I hope you don't want to do that either. I think we can all agree that that sounds really quite painful. So the good news is NumPy has a built-in function that will do this for us. So let's get started. I'm going to start by importing our favorite packages here. So I'm going to do import NumPy.
IMPORT.
Import
Space.
NumPy and NUMPY.
NUMPY. As NP.
It's suggesting the way I always type NumPy, but we're not going to do that at the moment.
Into.
All right, and you can hear I hit enter, and now it's saying you're on the second line. I'm going to do import pandas.
Import NumPy.
It wants to repeat import NumPy. We're not going to do that, but we're not going to need pandas at the moment, but we will need it very shortly. So let's just get it in here.
MPORT space PANDAS.
Import pandas.
In 3.
Whew, good news, all set and ready to go. So what I've just done is brought the NumPy and pandas packages into this coding session. All right. And next what we're going to do is we're going to use something called the linspace function. The linspace function is a built-in function in NumPy that will basically give us an evenly spaced array of numbers starting at a specified start number and ending at a specified stop number. I think this will be easiest to conceptualize if we actually do an example. So let's start by doing NumPy. So
NUMPY.
So from NumPy, so NumPy dot linspace, that's LIN SPACE. So basically, from the NumPy package, pull the linspace function, open parenthesis.
Left paren.
I'm going to do 0, comma 5,
5,
comma 5.
5. Right paren.
That's numpy.linspace, open parenthesis, 0, comma 5, comma 5. That first 0, that's our start value for the array. The second number, the 5, is the stop value for our array. And then that third number, 5, is the number of values I want. So basically what I'm saying is linspace, give me an array of numbers from 0 to 5, evenly spaced, and I want 5 of them. And when I hit enter, it's going to return to me an array of those numbers.
Out 3, array, 0, 1.25, 2.5, 3.75, 5.
And yep, there we go. And it has spit out an array that goes from 0 to 5, 5 numbers evenly spaced. Let's try this again. We can change the parameters. Let's try numpy.linspace.
NUMPY.
.linspace.
LINSPACE.
Open parenthesis.
Left paren.
I'm going to go 0, comma 10, comma 5.
0, comma 1, 0, comma 5.
What is this saying? It's saying our start value is 0, our stop value is 10, and I want 5 numbers. So numpy.linspace, open parenthesis, 0, comma 10, comma 5, close parenthesis. Give me 5 numbers evenly spaced from 0 to 10.
Out 4, array, 0, 2.5, 5, 7.5, 10.
And now you can hear we get an array of numbers going all the way up to 10 this time. Now this is almost what I said I wanted. I wanted an array of numbers from 0 to 10, but I wanted 100 of them. So this time we're just going to increase that third value from 5 to 100. So instead, give me 100 numbers evenly spaced from 0 to 10. And also, I don't want the computer to just spit it out at us. I actually want to save it. So just as Patrick taught us to save variables, this time instead of just doing numpy.linspace, I'm going to do x equals numpy.linspace because I'm going to say, hey, make this array of numbers from 0 to 10, 100 of them, and call it x.
X space equals space NUMPY dot LINSPACE. Left paren 0, comma 0, comma 1, 0, 0. Right paren.
X equals numpy.linspace, open parenthesis, 0, comma 10, comma 100, close parenthesis.
In 6.
And there's no output this time because we've just saved x, but if we type x and hit enter,
X X equals numpy dot
It wants to suggest that I repeat that same line from before. I don't want to repeat the same line. I just want to hit X and hit enter.
out 6. Array 0. 0.1010101. 0.2020202. 0.30.
All right, I'm not going to let it go through the whole thing, but as you can hear, it's spitting out a rather long array of numbers that are relatively close together, and it'll keep going all the way up to 10, 100 of them. We don't want to listen to all of that, or at least I don't. You're welcome to listen in your own time if you really want to hear all 100 of those numbers. But now we have checked that indeed, saved as X, we have an array of numbers evenly spaced from 0 to 10, and 100 of them, so rather small spaces. Now, I'm going to do something. I'm going to make one of these equations as an example so that you can see how roughly I've made these sort of simple shapes we have going. And then we'll load the CSV so that we just have all of the data. So what I'm going to do right now is I'm going to make something called a sine function, a sine of x. So what I mean by this is a sine function is a trig function, a trigonometric function. Basically, it's a wave. So as x increases, y responds to x by moving up and down in an even wave pattern. It just goes up and down at regular intervals as x goes up. So essentially what we are doing right now is we are making a wave shape. And I just want to call this y because this is how we often do this in math classes. So I'm going to call it y underscore sine to specify that we are making a sine function. It's always good to name your variables in such a way that you know what they mean. Because here y, if I just call it y, it could be like any function. If I call it y underscore sine, we know it's a sine, like a sine wave. So we are making a wave right now.
Y any line.
So y underscore sine, that's how we spell sine for in math. It's not like a sign, like a street sign.
SINE.
Y underscore sine, SINE, space equals space.
Space equals space.
And fortunately, NumPy, so sine is not an easy math thing to do, like a multiplication. It's something you generally want a calculator for. Fortunately, NumPy has a built-in sine function. So all we have to do is do NumPy dot, it's actually sin, so it's not the full sine, it's NumPy dot sin, and that's NumPy's sine function.
NUMPY. Left paren.
Whoops,
Dot sin. 2 star x.
That was a typo. It should be NumPy dot sign, not NumPy parenthesis.
Dot SIN. Left paren.
All right, now we want that left paren. So y underscore sine equals NumPy dot sin, open parenthesis, 2 times x. That's going to be 2 asterisk x.
2 star x. Right paren.
So we're saying that y sine is equal to the sine of 2 times x. Again, this is a really powerful thing about NumPy arrays, that you can do math with them like this. You can multiply them, you can take the sine of them, all sorts of things like this. And we can hit enter. And if we print out y sine now, so if I just type y underscore sine.
Y line SINE.
And hit enter.
Out 8. Array 0. 0.20064886, 0.39313661, 0.56963411, 0.72296256, 0.84688556, 0.93636273, 0.98775469, 0.99897117, 0.969555.
Sorry to play so many of those numbers for you, but I wanted you to hear that it goes up and then back down. If I'd let it play even longer, we would have heard it go all the way down below 0 and then back up again, which I encourage you to do because it'll give you an intuition for what's going on with this function. But essentially what I want you to understand is that a sine of x is a wave. So it's going to go up and then down and then up again and then down again. All right, cool. Let's make maybe one more really quite simple equation here. In fact, it's going to be the simplest equation. It's going to be a linear equation. We're going to make y equals x. which basically means that for every step x makes to get larger, y gets larger by the same amount. And I'm going to call this y underscore linear.
Y line.
Linear. Y underscore linear.
LINEAR space equals space.
And it's just y equals x. So y underscore linear equals x.
X.
And that's basically saying it's like a straight line just slanted upwards. Every step x gets bigger, y gets bigger by the same amount.
In 10.
And if we output y underscore linear,
Y line LINEAR out 10 array 0 0.1010101 0.2020202 0.3030.
all right, I'm going to stop it there, but maybe remember from when we printed out x that this is exactly the same. So basically we've just gone and we've made an array that makes the exact same, that is exactly the same as x. So every step x gets bigger, y stays the same amount, so it gets bigger by the same amount. It is a straight line. Now again, if you go to the curriculum, it goes through in absolute detail how to make every single one of the equations that we're going to load into this CSV. And so if you're mathematically minded or you just want to learn more about how to do math in Python, I definitely encourage you to check that out. It covers quadratic equations, all sorts of things like that. But we're not going to get into all of that right now just because I know it's a little bit tedious and everything's already loaded into a CSV. So if you're more on the data analysis side of things, you don't want to do all the math, then we don't have to get into all of that. Maybe, yeah, so I encourage you to check out the curriculum either at this moment to see the rest of the math happen, or to load the CSV, which I'm about to do. I actually, with the benefit of hindsight, I would love to show you guys how to do a quadratic equation as well, just because I want to show you guys how to do an exponent. Maybe this is the math person in me showing. So I'm just going to show you how to do a quadratic really quickly. Now this isn't actually the exact quadratic that I have in the CSV. I've sort of shifted and compressed that a little bit just to make it a nicer shape to listen to. And again, the curriculum goes into painstaking detail about how exactly that goes. But I just want to show you how to do an exponent. So a parabola is the shape of a quadratic equation. It's basically a curve that goes up, 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 really steep. As you get to the turning point, it sort of starts to level out. It turns around and then gets steeper and steeper as it goes back down or up again, depending on whether or not you flipped it. So it's almost like a wave, but it's not like the sine because the sine goes up and down repeatedly. The parabola is just a curve that turns over once, and it's steepest at the sides and flattest at the top. And it's the simplest form of a quadratic is y equals x squared. I'm going to save this as an equation or as a variable that I'm going to call y underscore parabola because that is the shape of a quadratic. So it's going to be y underscore
Y line
y underscore par ab y underscore parabola y underscore parabola space equals
space
x squared. And the main reason that I am taking the time to do this right now, even though it's all in that CSV, is that I want you guys to know how to do exponents I want to recap how to do exponents in Python, just in case, because I think it's good to know. So I always, when I started doing Python, expected an exponent to be a caret. It is not, it is 2 asterisks. So x squared is x asterisk 2.
X star 2.
So y parabola equals x asterisk 2.
In 12.
And if we print out y parabola just by typing it and hitting enter.
Y line out 12 array 0.0000000 e plus 00 1.020304005 times.
We get some crazy numbers. I don't find that easy to interpret. I don't know about you. I think they're all in a scientific notation. That's what that E means, that it's put it in the form of, so for instance, 9e2 would be 9 times 10 to the power of 2, which is 200. Not 200 is 100. Sorry about that. So 9 times 100 or 900. It's what we do for like really large or small numbers in science, and Python loves to print things out like that sometimes if it gets a little unwieldy. I don't know about you, but I find that a little bit difficult to interpret just listening to it. Scientific notation is a little bit hard to interpret just hearing it or looking at it, I would say. But the thing to keep in mind again is that a parabola, a quadratic equation, is that curve shape, going up and then down just once. And if you want to see the exact way I did this to make it in the CSV, then again, check out the curriculum. It goes into absolute detail about how I made this CSV so you can have all the nitty gritty. You can know the exact equation I used for everything. And again, if you're curious about that, feel free to stop by office hours or to shoot me an email. All right, I'm going to pop out of IPython and into Google Chrome, just
Sarah,
to copy and paste
a
that
unit
bit.
composite. Home. Untitled document. Change or remove link. Alert. Change content. Introduction to preparing. Introduction. Main landmark clickable readme.md region list.
And because
Equals.
I am low vision, I am well accustomed to squinting at my computer, so you might notice me navigating in a way that is a little bit more sighted than maybe just fully using NVDA. That's also a factor of me not
URL
being...
equal. Menu selected submenu. Non-visual data.
Me not being a full NVDA
Desktop
user.
with
I usually use Mac.
IPython.
So one little caveat, if you are working from the curriculum as it is now, there's one little thing we're going to need to do before we copy and paste that little snippet of code. Again, this is under the subheading just in case in the module preparing data for sonification. Now, I have done a little shorthand in this code snippet that in retrospect I shouldn't have, so I might go back and fix it. But basically, I am very accustomed to shortening pandas as PD. You'll see people do this a lot. It's just because it's shorter to type out than pandas. But we have to tell our computers, like, hey, I'm going to call pandas PD from now on. So we've already imported pandas, but we're actually going to import it again and tell the computer, actually, from now on, I'm going to call it PD. So that's just import.
IMPORT.
Import pandas.
Space PANDAS.
As PD.
Space AS.
PD.
D.
Import pandas as PD. So bring in pandas, and from now on, we're calling it PD. Again, we've already brought in pandas into this IPython session, but now we need to remind the computer, or tell the computer, hi, I'm calling it something different now. We only need to do this just because if you copy and paste straight from the code I put in the curriculum, I call pandas PD there, which was an oversight on my part, so I might go back and fix that. I probably ought to. So I'm going to hit enter.
In 14.
All right, we've imported pandas as PD, and now I am just going to paste in that line of code, or those 3 lines of code actually, actually there's one other thing we need to cover before we paste in those lines of code, and that's going to be something called astropy tables. Now, Astronify, the sonification package that we are using today, is a package that was made by astronomers to be used by astronomers. And we'll get into more detail about what exactly it is and how it works in a second. But because it was made by astronomers for astronomers, it uses a specific type of data, an object type in Python that astronomers like to use. This is something called an astropy table. Astropy is AstroPython, basically. It is a Python package that has a ton of astronomy functionalities. Things like astronomy units, like things like light years and parsecs. It also has coordinate system transforms. All sorts of things like that are handled within AstroPy. It also has a data type. Actually, there's multiple, but in this case, it has this type of object called a table. For our purposes here, an astropy table is exceptionally similar to a pandas data frame. And in fact, they're so similar that AstroPy has a built-in function to convert a pandas data frame directly to an AstroPy table. And the reason we're going to do this is because Astronify only takes as input AstroPy tables. It really just wants AstroPy tables because it was made for an astronomy data. So we have to convert our pandas data frame to an AstroPy table in order to give it to Astronify to sonify. So what I'm going to do here is I'm going to import table from AstroPy. So basically say, from this AstroPy package, bring in this table thing, because we need it. So I'm going to type from.
F-R-O-M.
So from AstroPy,
space.
That's A-S-T.
A-S-T.
R-O.
R-O.
P-Y.
P-Y.
Dot table.
Dot T-A-B-L-E.
So from the subsection of AstroPy, called table.
Space.
Import.
I-M-P-O-R-T.
So from astropy.table, import table, except here table is capitalized.
Space. T-A-B-L-E.
So from astropy table, import table. And again, the table, that second table, so not astropy.table, but that table after import, that's got to be a capital T there.
In 15.
All right, and it's imported. We've brought the table thing in. So if I bring in these lines of code, I'm just going to copy and paste those 3 lines of code in from under just in case. I'm sorry to all of you guys watching on the recording that I'm not reading this out. It is just a horrendously long URL. Maybe, should I read it out? Oh, no, I'm gonna really encourage you guys to go and copy and paste this from the curriculum, or maybe we can put it in the description of this YouTube video, because I think me reading it out loud right now is just going to lead to some suffering and also to just mistyping it. I don't think it's going to be very helpful. But there are 3 lines in this code. The first line that we're going to copy and paste in is URL equals that really long URL. It's basically, hey, the URL is called this, save it as this thing called URL. The second one is a function we've seen before. It's df equals pd.readcsv URL. So it's basically saying, make a new data frame called df, and then pd, remember that's now pandas, pandas.readcsv, so read the CSV at that URL. After URL, it's comma index underscore call equals 0. That means set the index of our new data frame as the 0th column. And then the third and final line of code is tbl equals table, so capital T table, that's the table we just imported from AstroPy, dot from pandas, open parenthesis, df, close parenthesis. What that's saying is make a new table, call it TBL, and make it from the pandas data frame that we've named df. All right, now I'll finally stop yammering and copy and paste that in. Well, I've already copied it.
Warning dialog warning, you are about to paste text that command prompt terminal IPython.
I trust, it was asking whether or not I trusted that copy and paste I was putting in, and I do trust it because that's my own URL. This is the moment we cross our fingers that it's going to work. Again, first line is the URL.
E/sonification, e selected, main/prepared data.csv, raw equals true selected, slash URL equal.
That's it reading that part of the URL, that's that first line.
df equals selected, space selected, pd.readcsv, URL index co, l equals 0, selected.
All right, and that's it reading the second line, df equals pd.read_csv, open parenthesis, URL, that's the URL from the first line, comma index call, comma index underscore call equals 0. And then finally, that last line,
tbl equals t selected, a selected, ble.fr selected, ompa selected.
All right, well, that wasn't very helpful, but That final line is TBL equals table, capital T, dot from pandas, open parenthesis DF, close parenthesis. So make a table from the pandas data frame DF and call it TBL. I'm going to hit enter and cross our fingers that it works.
In 16.
Whew, all right, no error messages read out. That means it worked. Success. All right, our data is prepared. It is in an AstroPy table. Let's take a moment to explore this AstroPy table. So first what we're going to do is we're going to print out the column names. The way we do this for an AstroPy table is by doing TBL, so that's the name of our table.
TBL.
And then we're going to do dot call.
Dot call names.
It's already trying to suggest it. Dot COL.
COL.
NAM.
NAMES.
TBL dot call names. COLNAMES. So from table, take the column names, and if we hit enter, it'll just print them out.
Out 16. X. Linear. NEG linear. Parabola. UBS. Sine. In 17.
All right, so in this table, there are 6 columns. There's X linear, neg underscore linear, parabola, abs, and sine. These are the X, actually the exact same X that we made with that linspace function above, and then 5 other functions of X, so variables that are following a function of X. Linear is that y equals x that we made above, so it's just every step that x makes to get bigger, y gets bigger by the same amount, so it's a straight line going up. Neg underscore linear is y equals negative x, so it's still a straight line, except every time that x gets bigger, y gets smaller, so it's a straight line slanted downwards. Parabola, that's the quadratic equation we were talking about. Now in this case, it's not exactly y equals x squared. It's a little bit different. I believe it's something like, if I recall correctly, I want to say it's, let me take a look. Y equals negative times the quantity x minus 5 squared plus 1. If any of you are algebra people, if not, don't worry about it. Essentially, what we care about here is not so much the math as the shape, so we understand the shape we're going to represent with sound. And remember, this is a curve that goes up, 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 up.
New notification from
no?
new notify Python.
Sorry. Someone's notification. Okay. What we care about here is that parabola is a curve that goes up really steep. Then as it starts to turn over, it gets a little bit flatter, stays flat, turns over, gets steeper again going down. Absolute value, what I've called abs, ABS, that is a function that goes up, 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 and then very sharply turns back down. So it's a straight line slanted upwards, kind of like our y equals x, and then it very sharply turns around and goes slanted downward in a straight line, like our y equals negative x. And then finally sine, that is our wave, so y equals sine of x, so that y goes up and down at regular intervals in a wave as x gets bigger. All right, so those are our 6 columns of the table. Next, let's just take a look at what's inside one of those columns. And the way we're going to call one of the columns of the table is a little bit different than the syntax you've been using with Patrick to call the columns of the pandas data frames, I believe. We're going to do TBL.
TBL.
So from table, what we've called our TBL, that's the name of our table. Open square bracket.
Left bracket, X.
It's already trying to suggest what we're going to do. Open bracket, we're going to do quotation mark.
Tick.
X. Quotation mark.
Tick.
And then close square bracket.
Right bracket.
So it's TBL, open square bracket, quotation mark, X, quotation mark, close square bracket. So basically, in X, or in table, we're calling the column called X, which is saved in quotation marks, sort of like how we do for pandas data frames. They've got quotation marks around them because they're a string, they're a word. And then if we hit enter.
Out 17. Less column name equals X type equals float 64 length equals 100 greater 0.0 0.101010101010101001 0.202020202020.
All right, I'm going to stop that there. I don't think we need to listen to the whole thing, but you might have noticed it was a little different at the beginning from how a panda's data frame prints out a column, but it tells you there's a column. The column name is called X. It tells you that it's a float, which means it's decimal numbers. It tells you the length of the column. I guess I wasn't paying enough attention. Hopefully it said 100 there because there should be 100 numbers. And then again, if you remember from before, those are the same numbers that were in our X array that we got from numpy.linspace. So, this AstroPy table has preserved the data that we made. And again, and then that we put in that CSV. And again, the curriculum goes through in detail every step of how we made this synthetic. So again, this not real data to represent shapes, put it in a data frame, and then get it into this AstroPy table that we now have. Awesome. So we know which columns are in our AstroPy table, and we've checked on one of the columns to make sure that it sounds.
New notification from move this new Python.
Sorry about that, folks. I'm borrowing a friend's laptop to do this since I am a Mac user primarily. And in fact, I don't even know how to put a Windows laptop on Do Not Disturb, so we might have some notifications coming in. Hopefully not too many. Okay, moving onwards. So we've checked on this AstroPy table. We've made sure it doesn't look fishy. Kind of is behaving for our purposes an awful lot like a panda's data frame. That's good news. That is all we really need to care about. And with that, we are going to check off that data preparation stage and celebrate because we are about to get into actually sonifying things. With one caveat. First, I want us to talk about what astronify is and how it works. All right, so astronify is a Python package we've installed that is developed by Scott Fleming at the Space Telescope Science Institute, Clara Brasser at Space Telescope Science Institute, and now at the University of St. Andrews, Jen Kotler at Space Telescope, and Kate Meredith at Glass Education. And it is a package designed to sonify or represent as sound a very specific type of astronomical data called a light curve. Light curves represent the observed amount of light from an object, typically a star, as we see it on Earth. So it measures the amount of light we see generally from a telescope, so how much light we are collecting from a telescope from a specific star over time. Astronomers like to call that observed amount of light, how much light we receive from an object here on Earth, we like to call that flux. So we are observing the flux, the amount of light seen, from a star over time. Thus, light curves allow astronomers to observe variability in the amount of light a telescope records coming from a star, or to record how bright a star basically appears to us on Earth. Observing this variability can give astronomers insight into all sorts of incredible phenomena, including explosive stellar activity called flares, so that would be a sudden increase in brightness at a period of time, and small periodic dips in the amount of light observed from a star caused by a planet orbiting that star and blocking some of its light as it passes through our line of sight and orbits the star, as it passes through our line of sight with the star. We call this latter phenomenon an exoplanet transit, and we've used it to discover thousands of planets outside our solar system orbiting other stars. What's essentially happening is that at regular intervals, as the planet orbits the star, it gets in between our telescope and the star and blocks a tiny fraction of the light, and it does that over and over and over again. So, if you see a star that looks like it's getting dimmer by a tiny regular amount at regular intervals, you can be like, there might be a planet getting in the way there, and boom, you found a planet. Astronify works by mapping the observed flux, again remember that's the observed amount of light we see from the star, that's our dependent variable that's changing with time, to pitch such that higher fluxes are represented by higher pitches. So if you have a moment where you observe more light, that data is going to be represented by a higher pitch. Each observation of the star's brightness is thus represented by a note where the pitch is controlled by the value of that observation. It is worth noting here that although it's the default to have brighter, like higher fluxes, brighter moments, brighter data points mapped to higher pitches, the user can set a parameter within Astronify to invert the pitches such that higher fluxes, more light, are mapped to lower pitches. There might be, personal preference reasons you might do that. We might get into discussing parameters involved in Astronify's sonifications next week, and this will hopefully make some more sense with some more examples. So I'm going to once again turn off NVDA's speech mode so it doesn't talk over the sonifications.
Speech mode off. Speech mode beeps.
Nope, I don't want it on
Speech
beeps.
mode Speech mode off.
All right, and I'm going to go to Astronify's example. This is straight from their webpage. I highly recommend that you check out Astronify's webpage. It's again linked on the curriculum. It's a really incredible project. I think it's great, so I highly recommend you check it out. And I'm going to play something. This is a sonification of a light curve containing a stellar flare. Did you hear that? Well, I'm going to play that one more time. All right, the sound stays relatively constant until, boom, there's this moment of woo, where it gets way higher pitched. And we know from the mapping we've just discussed that that higher pitch is representing a moment where the star gets a lot brighter as we see it. And that's the flare, a flare of light and activity from the star that we can really clearly hear as a change in the pitch of the sound representation of the data. All right, cool. Now, as a concept check, thinking back to our discussion of audification and parameter mapping, do you think that Astronify is parameter mapping or audification? I'll wait for a second. It's awkward to wait and give you a chance to think about it when there's no one on a Zoom call with me or anything. I'm just sort of yes. I sit in silence and I let people hopefully online think about it. Okay, that's probably enough time. So Astronify is parameter mapping because in this case the flux, or how high y goes up or down, our independent or our dependent variable, it goes up or down, is mapped to pitch. So it's not controlling the amplitude of the sound wave, which remember we perceive generally as volume. It's controlling the pitch. So that is a parameter mapping where we have mapped the flux to the parameter pitch in our sonification. All right, now here we've discussed Astronify within the context of its intended use, sonifying light curves. However, light curves are just a type of 1D data, or what I would call 1D data in astronomy. So we have two variables, time and flux, x and y. I suppose mathematicians might tell me that there are actually two dimensions, 2D, because it's time and flux, those are two dimensions. I'm going to call it 1D variable. Hopefully there are no mathematicians who are going to hunt me down for this. But there are all kinds of 1D data out there, including maybe some data that you've dealt with before. So we could realistically present other 1D data using Astronify beyond just light curves. But before we get to all that complicated stuff, let's go back to that sonification education point we were getting at before. And this was inspired by a talk that Scott Fleming, one of the developers of Astronify, gave at the Space Telescope Science Institute's Day of Accessibility, wherein he talked about sonification education and gave some examples where we sonify. Where he sonified with Astronify some of these simple shapes, very similar to what we're about to do. So now we're going to make our own sonifications. You're going to get a sense for what Astronify does. All right, I'm going to turn my volume down a little bit so I don't blast our ears out with NVDA.
Speech mode beeps. Speech mode talk.
I'm going to turn the volume up. Hopefully not too much. Hopefully that's a reasonable amount of volume. We'll hope for the best. Okay. We've installed Astronify, but we haven't imported it into this Python session. So what I'm going to do is I'm going to write from
F-R-O-M.
From Astronify.
Space.
That's A-S-T.
A-S-T.
R-O-N.
R-O-N. Nitha dot series.
See, it wants to finish for me, but I finish the sentence or finish the line for me, but I'm not gonna let it. From astronify. A-S-T-R-O-N-I-F-Y.
I-F-Y.
Dot series.
Dot S-E-R-I-E-S.
So from the subsection of astronify series, import, so space.
Space. I-M-P-O-R-T.
Import, and we're going to import a function called sona series. That is capital S.
S.
So capital S O
O
N I
N I
series. Capital S
S
E
E
R
R
I
E S.
So the S in sona and the S beginning series are capitalized. From astronify dot series, import sona series.
WX Python is not found for the current Python version. Pio will use a minimal GUI toolkit written with tkinter, if available. This toolkit has limited functionalities and is no more maintained or updated. If you want to use all of Pio's.
Alright, so I just let it play some of a warning that came out. I think a lot of people have been getting this warning. I've been getting this warning. I think Patrick did as well. I heard from some other people from the live class that they got this warning. Nothing to worry about. It's just like a little warning. Maybe bad advice, but I often ignore warnings if it's not an actual error message. So maybe don't take that to heart. But I just wanted you to hear it so that if you hear it on your computer, you don't worry. It's no biggie. And now we're going to get started with the sonification. Now, this is going to involve inherently some kind of repetitive 4 lines of code. I'm going to go through the first time or two relatively slowly, but then I encourage you, and then I'm going to get faster just to, so we don't take too much time. It's, again, all of these lines of code are on the online curriculum, so if you get lost, if I start moving too quickly at some point, just go and copy and paste it, because it's all a little bit repetitive. It's like the same thing with like one word changed, so there's no shame in like copying and pasting, as long as you understand what's going on and could do it yourself afterwards. But most programmers copy and paste, so. What we're going to do first is make an instance of a Sona series. So the Sona series is a class. We're going to make a Sona series object. I'm going to call it Soni_linear.
S-O-N-I.
S-O-N-I underscore linear.
Line. L-I-N-E-A-R.
Soni_linear. And I'm going to do equals.
Space. Equals.
And I'm going to do and the reason I'm calling it Soni linear is because this is going to be the sonification object, the Soni series object for our linear equation. So remember, that's our straight line going up.
Space.
Soni.
S-O-N-I.
Series.
S-E-R-I-E-S.
So remember, that's all one word with the S in Soni and the S in series both capitalized. Then open parenthesis.
Left paren.
TBL.
TBL.
So make a Soni series object from our table, which we've called TBL.
Comma.
Now there are 2 extra things we need to do here in this function. And that is we need to say, hey, Astronify, I know you're made for astronomers sonifying light curves, but actually, so I know that you expect these time columns and value columns to be like time and flux, but actually we don't have time and flux. We have like X and linear, that's the name of our columns. So we're just gonna tell Sona series, hey, expect time call, the time column, to be X, and val call to be linear, the value column. So that's TBL, comma, space, time.
T-I-M-E.
Underscore COL.
Line. C-O-L.
Equals.
Equals.
Open quotation mark.
Tick.
X.
X.
Close quotation mark.
Tick.
So say the time call is our X column. That's the name that we printed out above when we checked the column names in TBL.
Comma.
Comma.
Space.
Space. And then the value column, which is val call.
V-A-L.
Underscore.
Line.
C-O-L.
C-O-L.
Equals.
Equals.
Quotation mark.
Tick.
Linear.
L-I-N-E-A-R.
Close quotation mark.
Tick.
Close parenthesis.
Right paren.
Soni_linear equals Sona series with the S's capitalized, open parenthesis, TBL, comma, time underscore COL equals, open quotation mark, X, close quotation mark, comma, VAL underscore COL equals, open quotation mark, linear, close quotation mark, close parenthesis. Here's the next line. Well, we haven't actually played anything. We've just made the object. There's another little step I want to take. I want to say, hey, sonification, make the notes kind of a wider spacing. And this is something I've played around with already, and a choice that I've made. Again, remember how data representations involve a lot of choice. I'm increasing the note spacing here from the default, just so it's a little bit slower and easier to hear. So the way we're going to do it is we're going to do Sonic.
S-O-N-I. Line L-I-N-E-A-R.
SONI underscore linear, so our Sony linear object, the thing we just made, dot note underscore spacing.
Dot N-O-E.
That's note, N-O-T-E, underscore.
Line
S-P-A-C-I-N-G. Space equals.
Space equals space.
And I'm going to set it to 0.05. This is something that I have in advance tested and decided is a good note spacing for us. Again, choices we can make.
0.05.
All right. Sony underscore linear dot note spacing equals 0.05.
In 21.
All right, we've changed the note spacing. Now we're going to do Sony underscore linear.
S-O-N-I.
Underscore linear.
Line L-I-N-E-A-R.
Dot sonify. That means make the sound representation of this thing.
S-O-N-I-F-Y.
Open parenthesis, close parenthesis.
Left paren, right paren.
Because it's a function, but we don't have any parameters we want to put in. So Sony underscore linear dot sonify, make the sonification, make the sound representation.
In 22.
And the last thing we need to do is Sony underscore linear dot play, open parenthesis, close parenthesis.
S-O-N-I. Line L-I-N-E-A-R. Dot P-L-A-Y. Left paren, right paren.
All right, and this is the moment where I will once again turn off NVDA so it doesn't talk at us. You might get a warning that says like port MIDI closed. That's what NVDA is going to try to read for me. If you get that warning, don't worry about it. But I have...
Speech mode off.
I've turned off speech mode. I'm going to turn up my volume and I'm going to hit enter and it will play our sonification. Before we start, again, remember what we're sonifying. We're sonifying the shape of a straight line slanted upwards. So as x gets bigger, we should expect y to get bigger. And remember, y is mapped to pitch. Okay, I'm going to play that again. I'm just typing that same line again. Exact same thing, just so I can play it a second time. All right, can you hear that? The pitch gets higher and higher in a sort of straight line as we move along in time, which is the same as moving along that x value. You might hear this sort of wobble. That's just because there's like a little bit of a spacing. Again, that's actually the spacing I've done between the notes where I've spread them out, where there's a little bit of a space but some overlap between the notes, and your ears hear that as like kind of a wobble in the noise. But the pitch in general is going up in a straight line, representing that straight line.
Speech mode beeps. Speech mode talk.
All right, NVDA is back on. Turning the volume back down so we don't hurt my ears here. You've got plenty of time, so that's good. Let's sonify our negative linear equation. So that's the straight line slanted downwards. And I'm going to, this is the exact same lines of code, except instead of calling it Sony linear, I'm going to call it Sony underscore neg underscore linear. And instead of the value column being linear, it's going to be neg underscore linear, which is the name of that negative line column in the table. So let's repeat those same 4 lines of code.
S-O-N-I. Line. N-E-G. Line. L-I-N-E-A. R space equals.
So Sony underscore, S-O-N-I, underscore neg underscore linear equals space. Sony series.
S-O-N-I.
Again, remembering those capital S's.
S-E-R-I-E-S.
Sonus series, again, open parenthesis.
Left paren.
TBL.
T-B-L.
Make a sonus series from our table, TBL.
Comma.
Time call.
Space. I-M-E. Line. C-O-K-K-L.
Sorry, that should be time call. That K was an accident. Time call, so remember, it expects the x-axis, the independent variable, to be called time. We've called it.
Equals. Tick. X. Tick.
We've called it x.
Comma.
And our val call.
Space. A-L. Line. C-O-L.
Our value column.
Equals.
In this case is neglinear.
Tick. N-E-G. Line. L-I-N-E-A-R. Tick. Right paren.
Sony underscore neg underscore linear equals sonus series, open parenthesis, TBL, comma, time underscore COL equals open quotation mark X, close quotation mark, comma, val underscore call equals open quotation mark, neg underscore linear, close quotation mark, close parenthesis. Make a sonus series object from the table, call it Sony neg linear, where the time column is X and the value column is neg linear.
In 25.
All right, we're going to once again change the note spacing.
S-O-N-I. Line. N-E-G. Line. L-I-N-E-A-R.
Sony underscore neg underscore linear dot note underscore spacing.
Dot. N-O-T-E. Line. S-P-A-C-I-N-G. Space.
So Sony underscore neg underscore linear dot note underscore spacing equals
Space
0.05.
0.05.
That's the same as we did before.
In 26.
And then remember those last two lines.
S-O-N-I.
Sony underscore neg underscore linear.
Line. S-S-N-E-G. Line. L-I-N-E-A-R.
Sony underscore neg underscore linear dot sonify.
S-O-N-I-F-Y. Right paren.
Open and close parenthesis. We don't have anything in them. Sony underscore neg underscore linear dot sonify. Parentheses.
In 27.
And then the last line is that Sony underscore neg underscore linear dot play. Open parenthesis, close parenthesis.
S-O-N-I. Line. N-E-G. Line. L-I-N-E-A-R. Dot. P-L-A-Y. Right paren.
And I'm going to turn off NVDA again.
Speech mode off.
And I'm going to turn the volume up. And you can hear the pitch starts high and goes low. Let's play that again. I keep expecting to hear NVDA like read the line because I'm typing the same line again right now to play it again. And I expect it to speak to me, but of course I just turned speech off. So joke's on me. I guess that's my own fault. Sony underscore neg underscore linear to play it again. Excellent. All right, I'm going to do one more thing. You can hear, again, it goes much in the same way that Sony linear went up in a straight line. Here, the pitch goes down in a linear fashion. It goes down in a straight line with time because this is representing a line slanted downwards. All right, I'm going to do one more thing. I'm going to do Sony underscore linear dot play so you can hear that just sort of side by side. So this is that straight line slanted up. Sony underscore linear dot play just to play that straight line slanted upwards this time. Cool. Can you hear that? Yeah, it's going up. The pitch goes up this time instead of down. I feel like I can almost like feel it going up. Maybe that's sort of a weird thing to say. Maybe I've just listened to a lot of astronify sounds. It's kind of fun and spacey. I like these. They kind of feel like aliens in a fun way. I like it. All right, I'm going to turn speech mode back on.
Speech mode beeps. Speech mode talk.
And I'm going to remember to turn the volume down so we don't like pain anyone. All right, and what I'm going to do next is I'm going to sonify the sine wave function. Remember, that is our wave that goes up and down. Y equals sine of x, it's a wave that goes up and down. Now we are, again, this is the same 4 lines of code where we make the sonoseries object, we change the note spacing, we sonify it, and we hit play. And just with those couple of little differences, but because it's so similar, I'm going to start moving a little quicker. Again, all of this code is on the curriculum online. Feel free to copy and paste if you feel the need. I understand, but also make sure you understand what's going on. So this time I'm going to call it Sony underscore sine, S-I-N-E.
S-O-N-I, line, L-I-N-E, L.
I've called it Sony line. I actually want to call it Sony sine.
S-I-N-E.
All right, Sony underscore S-I-N-E space
equals space
equals sonoseries with those capital S's.
S-O-N-I-S-E-R-I-E-S.
Open parenthesis.
Left paren.
TBL.
TBL.
Comma.
Space.
Time call.
T-I-M-E.
Underscore
line,
call.
C-O-L equals.
Equals X in quotation marks.
Tick, X, tick.
Comma. Val call.
V-A-L.
Underscore call.
Line, C-O-L.
Equals sine. Because that's the name of the column with the sine function in our table. And again, if you don't remember, you can always just do tbl.callnames and hit enter to print out the list of column names in your table if you need to check.
Tick, S-I-N-E, tick.
And again, remember, sine is in quotation marks and it's spelled S-I-N-E.
Right paren.
And close the parenthesis or it'll throw an angry error.
In 31.
Changing the note spacing, Sony.sine.
S-O-N-I, line.
Sony underscore sign, sorry, not Sony.sine.
S-I-N-E.
Dot note spacing.
Dot N-O-T-E.
Underscore spacing.
Line, S-P-A-C-I-N-G.
Space equals.
Space equals, space.
0.05.
0.05.
Sony underscore sine dot note underscore spacing equals 0.05. Just move the notes a little further apart.
In 32.
Sony underscore sine dot sonify.
S-O-N-I, line, S-I-N-E, dot, S-I-I-O-N-I-F-Y.
Sony underscore sine dot sonify.
Left paren, right paren.
Make those parentheses.
In 33.
Hit enter. Sony underscore sine.
S-O-N-I, line, S-I-N-E.
Dot play.
Dot, P-L-A-Y. Left paren, right paren.
And we will do the same business of increasing the volume and turning off NVDA.
Speech mode off.
And hitting enter. That one's a lot more fun, right? I think that one's a lot more exciting than the straight lines. You can hear it go woo, woo, woo as that wave goes up and down. So as Y gets higher and then lower, the pitch goes up and down at regular intervals. I'm going to play that one again, actually, because I really quite like that one. So just typing that same line, Sony underscore sine dot play. Cool. That's our sine wave. We've played 2 different lines, one going up, one going down, and we've also played our sine wave. Let's turn the volume back down.
Speech mode beeps. Speech mode talk.
All right, there are just two more functions to sonify here. They are our quadratic or our parabola. So again, that's the curve that starts steep, turns over once, a little bit smoother at the top, and then turns back downwards and gets really steep again. And then also our absolute value function, which goes up in a straight line, very sharply turns back around and goes right back down. The goal here is I want to sonify these two. I'm going to play them actually side by side. So I'm going to make both sonifications, wait to play them until they're side by side, because I want you guys to learn to hear the difference between a sharp turnaround and a more gradual turnaround. So a more gradual turnaround in our parabola, which is a smoother curve, and then a really sharp turnaround in the absolute value. And again, we're going to move a little quickly through the code here, so feel free to copy and paste or to check the curriculum if you need to. So that's, I'm going to call this Sony underscore parabola.
S-O-N-I line.
Parabola.
P-A-R-A-B-O-L-A.
Parabola is P-A-R-A-B-O-L-A. Space equals.
Space.
Equals space. And then it's sonoseries.
S-O-N-I-S-E-R-I-E-S.
Not forgetting those capital S's.
Left paren, T-B-L.
Open the parenthesis, table, time.
M-E, line, O-L.
Time underscore call equals X.
Tick, X, tick.
With X in quotation
Comma.
marks. Another comma.
Space, V.
V-A-L.
Line, C-O-L.
Val call equals.
Tick.
And here it is called parabola is the name of the column.
P-A-R-A-B-O-L-A. Tick, right paren, in 36.
All right, we've made our parabola sonoseries. We're going to change the note spacing.
S-O-N-I, line, P-A-R-A-B-O-A, dot, N-O-T-E, line, F-P-A-C-I-N-G.
Sonnet underscore parabola dot note underscore spacing. Space equals space.
Space.
Space equals space 0.05.
0.05.
Same as before, just doing that because that's what I tested and I think sounds best. Feel free to change that note spacing, make it bigger or smaller, and see what you think.
In 37.
Again, that's tweaking with the parameters of the sonification to see what you prefer. Again, full of choices. Then sona underscore parabola.
S-O-N-I, line, P-A-R-A-B-O-L-A.
Dot sonify.
Dot.
So make the sound representation.
S-O-N-I-F-Y. Right paren.
And I'm going to hit
in
enter.
38.
But I'm not going to do Sony underscore parabola dot play just yet, because again, I want to sonify the absolute value thing at the function at the same time. So let's do that really quick. I'm going to call that Sony underscore abs, ABS, because Sony underscore absolute underscore value sounds really painful to type out. So abs.
S-O-N-I.
Underscore abs.
Line, A-B-S. Space.
Space equals space. Sony underscore abs. Space equals space. Sona series with the capital S's.
Space. S-O-N-I-S-E-R-I-E-S.
Sona series.
Left paren.
Open the parenthesis. TBL.
TBL, comma.
Time call.
Space. I-M-E. Line. C-O-L equals.
Time underscore call equals X.
Tick, X, tick.
Remembering our quotation marks.
Comma. Space, A-L.
V-A-L, val call.
Line, V-O-V-C-O-L.
Made a typo there. V-A-L underscore C-O-L. I feel like that's kind of easy to make a typo on. Equals abs, because that's also what the name of that column is, because I guess I never wanted to type absolute value, so I just called everything abs.
Tick, A-B-S, tick. Right paren.
So Sony underscore abs equals Sona series, open parenthesis, TBL, comma, time underscore call equals open tick, or open quotation mark, X, close quotation mark, comma, val underscore call equals open quotation mark abs close quotation mark close parenthesis.
In 39.
Soni underscore abs dot note spacing. We're changing the note spacing.
S-O-N-I dot A-B-S.
Nope, I did.
Dot A-B-S equals Sony.
I did Soni dot abs. I meant to do Soni underscore abs.
Line A-B-S space space.
Nope, I did space. I want to do Soni underscore abs dot note spacing. Sorry, my brain is apparently leaving me.
Dot N-O-T-E line F-P-A-C-I-N-G.
Soni underscore abs dot note underscore spacing equals 0.05.
Space 0.05.
All right.
In 40.
And then Soni underscore abs.
S-O-N-I line A-B-S.
Dot sonify.
S-O-N-I-F-Y. Left paren, right paren.
Open and close the parenthesis.
In 41.
And now we can play the parabola, so that smooth curve going up and then turning around going down, next to the absolute value, which is that sharp turnaround like the top of a triangle. So first I'm going to do the parabola.
S-O-N-I.
So that's Soni underscore parabola dot play.
Line P-A-R-A-B-O-L-A dot P-F-A-Y. Left right paren.
Soni underscore parabola dot play, open and close the parenthesis, and again, turning off NVDA.
Speech mode off.
Turning up the volume, and hitting enter. Oh no! We have an error?
Speech mode beeps. Speech mode talk.
This is terrible.
O-N-I line A-B-S dot P-L-A-Y. Left per right paren. PIO warning. Port MIDI closed. In 43.
Interesting. I got an error when I tried to play the parabola, but the absolute value seems to have played. Let me try the parabola again.
S-O-N-I line A-P-A-B-O-L-A dot P-L-A-Y. Left right paren.
That's Soni underscore parabola dot play, open parenthesis, close parenthesis. I'm going to turn off NVDA and hope it works this time.
Speech mode off.
Alright, I guess it will work this time. I guess it was just angry before. I'm going to turn NVDA back on so I can play the absolute value again.
Speech mode beeps. Speech mode talk.
That's going to be Soni underscore abs.
S-O-N-I line A-B-S dot P-L-A-Y. Left paren, right paren. Speech mode off.
So that's Soni underscore abs dot play. You're going up, 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 and then suddenly changing and going back down at a constant rate. Let me play the parabola one last time so you can hear them side by side again. Again, that's Soni underscore parabola dot play, open and close the parenthesis. It's a much slower change to the pitch turning and going back down. We are literally hearing the difference in those shapes, a sharp versus a slow turnaround. I encourage you to play that often on your end just until you get that sound for it, the feeling for it. And again, play all of the sonifications again and again. I'm going to play the sine again. Soni underscore sine dot play. We can hear that wave pattern going up and down that we don't have in that absolute value or the parabola. There's more turnarounds in the pitch going up and down than we have in those other two shapes. So again, the goal here is to develop an intuition for what Astronify is doing and how different shapes, how different behaviors of our data. Because again, this is all about a representation of the data. It's what is this Y doing as X changes, which we have represented as what is the pitch doing as time changes. It's developing this intuition for what is going to happen to our data representation for different types of data behavior. That is the goal here. That is all about what this education process is about. This is what we teach people to do with data visualization for years, and what we're just developing an intuition for now. This is where I'm going to conclude the fourth tutorial from this non-visual data science tutorial series. This is the first of 2 sonification tutorials and the fourth of 5 total tutorials. So next week we'll pick up with more data sonification using Astronify, getting with some more realistic data. I'm really excited to see you there. I'm excited to do more sonification with you. Again, we're very grateful to Pandas and NumFocus for generously supporting this tutorial series. And I encourage you, if you have questions, to reach out to me or Patrick via email, or to come to our office hours. Same Zoom link as the tutorials, 6 to 8 p.m. UK time on Zoom. And also to check out our curriculum online where all of this code is hosted. Yeah, thank you so much for coming. Excited to talk more sonification with you all next week, hopefully in a live recording if the sound permits. All right, thanks all. I'm just gonna wait a few seconds because I'm worried the recording is gonna like cut off the last few seconds, and I don't want it to cut off like the actual end. So if this is still in the video, sorry for this like awkward few extra seconds where I'll like wave at the camera and sort of ramble on. Rambling. Also crossing my fingers that the recording worked, because if that didn't work, I'll be quite sad. And I guess sit here for 2 more hours, which would make me quite sad. So fingers crossed, everyone. I suppose if you're seeing me still rambling here, then it's worked. All right, I think that's probably enough time. I'm gonna go. Stop recording.